Hi everyone, thanks for coming to my presentation. So in this talk, I'll talk about the lessons learned from automatically optimizing databases using machine learning in the real world. I'm Bohan and from OtterTune. If you are not familiar with OtterTune, it's a startup focused on optimizing databases automatically with machine learning. We are focused on a specific sample Postgres and MySQL. It's based on many years of research from Carnegie Mellon Database Group, led by Professor Andy Powell, Dr. Dana Vick, and myself. Okay, let's get started. So I will introduce the background of database automatic tuning first. Then I will introduce the real-world scenario and discuss the lessons learned. And at last, I will talk about the large language models for the database optimization. So that's a super hot topic these days. Okay, so background. So databases are notoriously complex to deploy, maintain, and optimize. There are many aspects of databases to optimize. For example, you need to design your schema, physical design, like design your indexes and table partition. You need to optimize your knob configurations and optimize your queries. And you also need to provision your hardware. So it's very hard to maintain and optimize. And human experts are also very unscalable and expensive. So that's the statistics for the average salary for US DBA is like the average salary is like $96,000. So human experts are very expensive these days. And even if you have money, it's still really hard to find a good DBA these days. And so to solve this issue, there are lots of research and efforts from both the academic and industry to solve this issue. So there is a long history of attempts for automating the database management and optimizations. So from 1970s, it's called self-adaptive databases. And in 1990s and 2000s, it's called self-tuning databases. And these days, it's called self-driving databases. So here's a paper published from Carnegie Mellon Database Group in SEDAR 2017. So we introduced self-driving databases. And later, Oracle announced its world-first self-driving autonomous databases. So research in the last decade are focused on applying machine learning models to solve the database tuning problem. So there are many aspects of a database you can optimize using machine learning. For example, you can optimize your indexes, optimize your table partitions. You can also optimize your knob configurations and query optimizations. There are tons of the research and work related to that. So the idea is that you have an application database, and then you have basically you have an agent to collect your performance data from a database. Usually it's metrics data, like CPU usage and your schema data, query data, etc. So you collect those data and use those data as a training data to train a machine learning model, and use the machine learning model to recommend to make recommendations and apply recommendations to your databases. Sorry. So OtterTune is an automated database tuning and resource optimization platform. So it's based on many years of research from Carnegie Mellon Database Group, and it uses machine learning to automatically optimize your databases to improve your performance and cut cost and maintain healthy operations. So we start from in the research, we start from knob tuning. So we published a paper in Sigma in 2017. It's only focused on knob tuning. But in the commercial version, we extend to many other aspects of optimizations, including knobs, indexes, query, and hardware provisioning. So we support Amazon RDS and Aurora for Postgres and MySQL. So let's talk about the real-world scenarios. Because we did many years of research in a university, and we apply it to the real-world scenarios. We found many things are different, actually, in the real world. So the first challenge we are facing is that in the real world, users do not usually maintain a suitable staging database. So in a university, in a research, we assume users have a similar staging database, which has a similar workload and similar data as a production database. So in research, we basically tune the staging databases using machine learning, and then we verify that the recommendation works in a staging environment, and then apply it to the production workload. But in the real world, we do not have such a staging database. Because in the real world, the staging databases are usually running on smaller hardware and with a smaller data size, and the workload is usually much simpler than a production database. So in this case, when we use a machine learning model to optimize your staging database, it's very different from your production database. So we cannot apply the recommendation from staging database to your production database directly. And so then there are two ways to solve this. The first way is that you can just tune the production database directly, which is really dangerous, right? Because if you make a bad recommendation, it can crash your server. So the second way is that we can probably create a similar staging database, suitable staging database by ourselves, but data, we will discuss later, where we find it is also not very realistic in the real world. So the second challenge is that user cannot capture workload and replay them. So, so if you want to create a staging database by yourself, it's easy to create a copy of your it's easy to create a copy of your production database. It's really easy in a cloud environment. You just click some buttons to clone a production database, but it's really hard to replay capture a production workload and replay them on your staging environment, right? Because tools for open source databases like Postgres and MySQL, they are not very sophisticated. I think Percona has a replay tool for MySQL, but we use that. It's not very sophisticated. Instead, I think Oracle has very good tools for this for such use cases. But for open source databases like Postgres and MySQL, we don't have such a good tools for workload replay and capture. And another way is that if you can use the built-in store query log, the idea is that you can log all your queries into a query log. I think Postgres and MySQL, they both support that. But the thing is that it's very expensive in the real world, in the production, because you need to write all the read queries and write queries to disk. And it's super expensive because you need to write all the queries to the disk. Actually, we tried that once, and the CPU usage increased from 5% to above 90% in production. So it's really not a good way in production. So that's the second challenge we are facing. Again, in the research, we did that for Oracle, and Oracle has a very good tool for capture workload and replay them. But in the real world, for Postgres and MySQL, we just cannot do this. The third challenge is that we found the production workload is always dynamic. So it makes the machine learning model super hard to know whether the performance change is caused by the workload pattern changes or caused by our recommendation. So in this example, I think this is the throughput. It's a queries per second over time. You can see at this time range, the throughput increases by 25%. But the thing is that we don't know whether it's because of the workload change, because of the traffic increase, or because of we make a recommendation and makes the performance better. So we don't know because the workload is dynamic in the real world. So we don't know it's because of a workload change or because of the recommendations we made. So in the research, we just do the experiment with the benchmark like TBCC, and it's always static. So then in the research, we know if the throughput increases, we know it's because of our recommendations. But in the real world, the workload is always changing, so we don't know whether it's because of our recommendations or because of the workload change. That's the third challenge we are facing in the real world. So now I will talk about lessons learned and how we address the challenges I mentioned above. So since we don't have a suitable staging databases, and we also cannot capture workload and repeat them in production, so we are thinking about, can we just tune the production database directly? And it actually most customers allow us to do that, but we need to do that very carefully under some conditions. They need to have control over what, when, and why changes are applied. So it needs to be very careful because that's a production database. So they need to have control over when to apply and why we should apply such changes. We'll talk about this later in detail. And we also find that production workload is always dynamic. But another thing is that we also found most production workloads, actually they have the daily or weekly pattern. For example, your traffic is large in a day, and it will be low in the night. And it might be, the traffic might be high in the workdays and maybe low in the weekends. So we find most workloads have such daily or weekly patterns. So then we actually can use the machine learning models to learn these patterns. And then we know when the workload will change. And then we know the performance changes because of the workload change or because of our recommendation. It's not 100% accurate, but it can, I think, in most cases, it's good enough. So since we will tune your production database directly, the user need to we need to be very careful and to reduce the degradation of your production database. So a tuning service must provide control to users to allow them to specify what and when and why the service will optimize the database. So the example is that they need to specify the tuning period, like how often we will make recommendations and apply such recommendations. We also need to specify the knob bounds, the parameter bounds for tuning. They also need to specify the scheduling. So usually users will apply such changes in the working hours in weekdays instead of weekend. And they also need to approve the change. They need to we will show the change to users first, and if they think it's right, they will approve that instead of just apply it by ourselves, which is a human-in-the-loop approval. Also, to help build the trust, users will need to know why we apply such changes. So for example, if we make a recommendation to change a parameter value, users need to know why we set the parameter to that value. Then you need to specifically know why we make such changes. So that's why we provide some data-driven explanations about recommendations. So one simple example is that if the machine learning model recommends you increase the buffer pool size, and we find that you have high cache miss ratio, and high cache miss ratio means you don't have enough buffer pool size. So we explain to user that's why we recommend you to increase the buffer pool size. That's a very simple example, but you get the idea. And another thing is that we found that machine learning model and domain knowledge, you don't need to pick just one, because they both have pros and cons. So in OtterTune, we actually integrate both methods to recommend to have better recommendations. And for machine learning models, the pro is that it can find nearly optimal database configurations, and the recommendations is nearly optimal. But the challenge is that it's really hard to explain the recommendation because it's just recommended by machine learning model. If you ask me why it makes such recommendation, I don't know, because it's a model. And it solves. Yeah, and it also needs training data and need time to converge to find the optimal configuration. So that's the challenge for machine learning model. But the good thing is that it can help you find the optimal, nearly optimal configuration and recommendation. And for the heuristic-based approaches using domain knowledge, it may not yield the best recommendation. But the good thing is that it can provide explanations about recommendations. It can explain why you make such recommendation based on your domain knowledge, database domain knowledge. And it also does not need the training data. So you can recommend it directly without training data and without, you can recommend it immediately to users. So the idea is that we combine those two approaches together, right? Because for example, we can use a machine learning model to help you find the optimal database recommendation, but we can also try to use the domain knowledge to explain why it makes such recommendations. Another example is that we can use the domain knowledge to recommend some good configuration to you at the first stage, because it does not need the training data. And after we have more training data, we can then use machine learning models to make the optimal recommendation to you. And users, actually, they don't care about whether it's recommended by machine learning or the domain knowledge. As long as it's a good recommendation and you explain why we make such recommendations, it's good enough for them. They really don't know about whether it's AI or the domain knowledge. Or, as long as it's good and as long as it has explanation on that, they will use that. And the last thing is that we found that it's not only a machine learning problem. Because as I said, automated database tuning actually works better in the real world compared to research type. But getting the full benefits of these optimizations and tuning production database safely is not only a machine learning problem. So all the things I mentioned above, like allow user to specify null bounds, allow user to specify tuning period schedule, and make the data-driven explanations, they are all engineering efforts to help users to tune production database safely. Those are not related to any machine learning models, but those are really important in the real world tuning service. We also did some research and published a paper in LDB 2021. And we did the real world test use case for Société Générale. It's a very large French bank. And we also tried the three models, machine learning models, which is Gaussian process regression, a deep neural network, and DDPG, which is a reinforcement learning model. And the thing is that we found they all use the similar performance. Probably the deep neural network is the best, but actually the difference is really, really small between those models. So that's why we think the machine learning model is not the hardest part, because the hardest part is that how to safely use a machine learning model to tune your production database. That's the hard part for us. OK, so that's part I will talk about the large language models for database optimizations. We did some explorations on that, and we have some findings, initial findings. So large language models that ChatGPT that super hot these days, and everyone is talking about that. And we try to apply those to database problems. And the first thing we are trying to do is that if we can ask some database-related questions to LLM, to ChatGPT, we find that it might not be the ideal resource for addressing your database-related problems, because it can give you inaccurate answers. Yeah, most times. So for example, I asked about the JIT-related knobs in Postgres. JIT is just-in-time compilation. It's a feature in Postgres. I asked about this knob, and it gave me 4 allowing values for this knob. It can be off, which disable the JIT feature, and on, which enable JIT feature, and normal, and they also have explanation on that. enable JIT accommodation for statements considered worthwhile by the query planner. Or they also have explanation on that. It looks right, but actually in Postgres, they don't have these two options, and they only have these two options. This is just a simple example. I try to ask TiDB many questions. Sometimes it looks right, but it's not actually accurate. So I don't think you want to rely on ChatGPT to answer your database-related questions.
What kind of GPT model behind the TiDB you are using for the questions?
It's 3.5.
Okay.
Thank you. Sorry. Another thing we are trying to do is that if we can ask the database optimization problem for ChatGPT, that ChatGPT optimize database for us. So the thing we found is that ChatGPT are trained on existing text and cannot account for an application's workload patterns. So it can basically give you some high-level ideas, some generic recommendations, but it cannot give you exact answers for your specific database and for a specific workload. So the example we use is that it's a knob option in MySQL in the DB adaptive hash index. Basically, it allow MySQL to build a hash index in buffer pool. We ask ChatGPT whether we should enable it or not, and we give it as the workload pattern. We have like 70%, 77% are stack queries, and others are write queries. We give them our workload pattern. Basically said, okay, it's whether or not to enable this option depends on your workload. Since you are really heavy, you can probably benefit from it. So you can probably enable it. However, it's important to know that this setting can also consume additional memory and CPU usage to give you the overhead. In some cases, it can lead to the connection issue and degrade your performance. And it tells me that before you decided to enable it or not, you should test it in your environment. So basically, it says you can enable it, but it may also give you some overhead on that, and you should test it. So it's generally, but I still don't know the answer, because it does not give you an exact answer where I should enable it or not. And also, in many cases, we found that their recommendations are not accurate and are often wrong. But the good thing is that we found ChatGPT is very good at queries, the database queries. I think it's because of the ChatGPT trained on a very large text data size and query code data size. So it's actually very good at writing queries. So in these examples, I asked ChatGPT to rewrite this query. The original query is a stack star from a table where ID equals 1, or ID equals 2, or ID equals 3. And I tell ChatGPT to rewrite this query using in operators. And it rewrite it to ID in 1, 2, 3. So we actually published for OtterTune about that because we found in Postgres, in many cases, the in operator is much faster than all operator. So that's why we tell ChatGPT to rewrite this query. And in most cases, it can rewrite it correctly. But you need to tell ChatGPT how to rewrite it, right? Because in this example, we tell ChatGPT to use the in operator. So then it rewrite it correctly. So it can help your rewrite queries, but you need to give them a hint how to rewrite it. I think that's the end of talk. And if you want to try to train your Postgres and MySQL on Postgres and MySQL on Amazon, you can go to our website and try it for free. And I'm happy to answer any questions. And I'm also around, so if you have any questions, we can also discuss off that. Yeah. Thank you.